So welcome everybody to this webinar that we have on LiDAR technologies, integrated photonics for LiDAR. This is a webinar is part of a series of webinars that we try to hold at regular intervals, a whole range of applications and also on the tools that are used therein. And so feel free to check our website for topics of interest, and we are always welcome we're always happy to have you as part of our webinars. So for those, I know I recognize actually quite many faces here, so people we know already, but also some new names. And for those that are new and I don't know Luceda very much, allow us to just have one slide about Luceda. That's all that you will hear about the generic company today, and the rest will all be about technology and the tools. So Luceda Photonics is a company based in Belgium, and as you know, Belgium has a very, very, very strong integrated photonics ecosystem, mainly based around the University of Ghent, that has a very strong research group, and imec. And we as a company are a product of that ecosystem as well. The name, Luceda, stands for LUS. LUS is the Latin base for light, and EDA is the acronym for electronic design automation. So the mission is really in the name. We are the design automation tool for light, so Luceda. Our mission is to help photonic IC designers enjoy the same power as electronic IC designers. Enable designers to make great photonic chips in record time that work. And we pride ourselves that we are very human-centric and that we know what we talk about. So that we are experts in photonics. So today we have a great line of speakers for you today that all can show how LiDAR and photonics are a match made in heaven. So first we have Dr. Sarp Kerman, which is the CEO of a company called Xsilight. And Xsilight is a fresh startup that was founded, I believe, in 2021 in Shanghai, in China, with the idea of commercializing miniature LiDAR modules with no mechanical component. Sarp is a veteran in photonics, more than 10 years of experience in integrated photonics. Besides Xsilight, he's also continuing his role as director of the PIC department at C3, also since July 2021, where he's contributing to the research on PICs for healthcare applications. As part of his education, Sarp has received a PhD in physics from the University of Leuven in 2017, and for his research most on healthcare applications at imec. His professional interests are obviously integrated photonics, 4D sensing, PIC for healthcare, transceivers. And in his earlier life, he also had a stay at Sequoia, where he designed transceivers. So he's really an all-over-the-board photonics designer and entrepreneur. So we are really happy to have him here. And he will talk about LiDAR as a technology and also as specifically how it's implemented in photonics. Then we have Amin, Abbasi. He has a PhD from the University of Ghent University on hybrid laser integration, integrated photonics, I believe mostly DFB lasers. Currently, he has a role of business development manager at imec, taking care of all photonic related applications, including LiDAR, quantum computing, and biophotonics. So he really has a bird's eye view on everything that is actually done in R&D, and I'm sure he will give a very interesting perspective on how fabrication affects the performance of LiDAR systems as well. And finally, we have Chiara, our product marketing manager at Luceda Photonics. She also holds a PhD, so it's all on PhDs only as speakers, as it seems. Also from imec in graphene electro-absorption modulators on silicon. At Luceda, Chiara is leading our global marketing efforts. Having engaging stories like this one on LiDAR is also that our role to help put to reality. And then finally, myself, I'm not a speaker, but I quickly introduce myself. My name is Pierre. I'm one of the founders of Luceda Photonics. And I also have a PhD in integrated photonics, focusing on integrated photonics, integrated low energy photodetectors. This is the plan for today. So after these 5 minutes of introduction, which turned out to be 6, Sarp will introduce the roadmap to commercialization of on-chip LiDAR for automotive industry. It's a 20-minute talk where I think it's automotive industry. It's a 20-minute talk that covers the basics, but also that gets into the applications. And then Amin is gonna talk about the fabrication challenges for LiDAR and how the imec platform addresses them. And then finally, Chiara will talk about the design tools that are utilized to design systems that are part of some LiDAR systems, which is optical phase arrays or OPAs. And this will be a demonstration on how the design tools actually help the industry as a whole. After that, there will be a Q&A session where you can ask whatever you want to anybody in the room, including the participants. So we really mean it as being as interactive as possible. So don't be shy, ask questions in the chat or using your voice at any time, and we will make sure that the person that are addressed to gets the opportunity to engage. That's it for me. So now the floor is to Sarp, that I want to thank again for contributing to our webinar today. The floor is yours, Sarp.
Thank you very much for the introduction, Pierre. So let me start by sharing my screen. Can you see my screen?
Yes.
Okay, great.
It's not full screen yet.
Yeah. Okay. So let me just minimize this as well. All right. Hi, everyone. I'm Sarp Kerman, and as Pierre mentioned before, I'm the CEO of Xsilight. It's a fresh company based on integrated photonics LiDAR. And today I'm going to talk about the roadmap to the commercialization of on-chip LiDAR for automotive industry. So let's start with what is LiDAR and why are we using LiDAR and who is doing LiDAR and where. And then I'm going to go more towards integrated photonics LiDAR and the challenges and the progress and what we are doing in Xsilight on this topic. So when we think about distance and how we perceive distance, we should actually also think about objects that we see around, which requires years and years of knowledge and information. For example, when we look at this picture, we see some buildings. And how do you know that they are buildings? They carry a certain shape, such as a rooftop and a few windows around and a door possibly. And we see a road. And our brain tells us that, okay, this house is smaller, so it must be further away. And there's a continuation of houses and road, and the road also becomes smaller and smaller. So then we have a certain understanding of distance. But if we don't have this kind of information of what a house looks like, or we don't know that this road is continuous here, our mind would get boggled by the distance of things. So you can see at the picture on the right-hand side, for example, such a scenario. A machine sees the world the same way if it doesn't have any information about the how the objects look like, or if there's any continuation or not. So, of course, this kind of learning curve requires a lot of computational power. And at the end of the day, what we want is being able to tell on a road in a car that this is a road, there's an obstruction, and there are other vehicles around, such as a truck. So, but to be able to do that, computational power is one thing, but we can reduce the need for this computational power by having a better sensor. So in this case, actually, if we had a sensor that could detect the distance of every single point on this view, then we wouldn't need such a high computational power. Or we could use this computational power for other things, for image recognition in that 3D point cloud. So here, what I described is, of course, LiDAR that gives us the 3D image, 3D point cloud of what we see in this view. So on the left-hand side, you see an image, LiDAR image of a rotating basketball. And here, we see the distance of every single point on this ball. And apart from that, thanks to FMCW technique, we see that the positive velocity on the right-hand side and negative velocity on the left-hand side of this ball, which indicates that it's rotating. So we can actually detect speed of every single point on an object. We could directly tell the speed of this truck as well as this distance, which is going to be essential for self-driving cars. So when we talk about LiDAR market, of course, I don't want to limit things to a single market such as ADAS vehicles or robotic vehicles. I want to categorize the applications in two main groups. One is 3D modeling and the other one is robotics, in my opinion. Under 3D modeling, we can think of 3D printing applications where we have several micron resolution with a LiDAR, or city planning where we scan huge buildings or streets, or we can think about failure detection where we scan certain objects like cars, or agriculture applications where we scan farms. And when we think about robotics applications, it can very well be, as I mentioned before, ADAS applications where we actually prevent collision, or drone automation where several drones fly around and do delivery automatically without any need for a pilot, or logistically applications where you have seen videos of Amazon factories, I believe. So there are a lot of robots that are going around, bringing one piece of box to another place. We can make this actually much faster. We can increase the throughput. And of course, humanoid robots, animal or insect-like robots, and hopefully they won't end up like Terminators. So, however, still, when we look at the market growth, the nearest technology with highest yield in terms of money is going to be ADAS vehicles, because we want to have self-driving cars and we want to stop having also any kind of collision in traffic. And thanks to this kind of growth, there are a lot of startups popping around at the moment. And most of them are in US. And there are some in Europe and some in Israel. And of course, some in Asia as well, relatively lower number than US. And we started in Shanghai as Xsilight last year, as Pierre mentioned before. So I will give a brief introduction about different LiDAR platforms and why integrated photonics platform is important. But first, let's start with the detection methods that we can use for LiDAR. The most common method at the moment is using pulse LiDAR, which is DTOF, where we send a pulse train to objects and receive it back and directly compare the time that has passed in between. However, this technique requires high-speed electronics because light is fast. And when there are plenty of LiDARs around, it causes crosstalk. We can actually mitigate the need for complex high-speed electronics by modulating the light like a sinusoidal way and cross-correlating the light that we send and the signal that we receive. It gives us better resolution, but still, due to the periodic nature of the signal, there's the distance ambiguity, and we would need more integration time and power, and still subject to interference. And what we can do in terms of amplitude domain is we can randomize the amplitude of the signal to at least get rid of the interference effects or crosstalk effects from other LiDARs. That technique works, however, it requires more integration time and power. What I'm going to focus on for the rest of my talk is FMCW, frequency modulated continuous wave LiDARs, where we use a source and split the signal from the source into two, while one part goes to an object, another part stays inside our device as a local oscillator. And when the light comes back from the object, we interfere that light with local oscillator and detect by balance photodetector. So by the nature of interference, we are actually amplifying the signal. The signal that we observe in a balanced photodetector is proportional to the square root of the total loss that the light has observed from source to object and back. While in direct detection techniques, it's directly proportional. So what this means is if we are getting 1 in a million photons back in a direct detection, here we get a penalty of 1 in 1,000. So this is actually 1,000 times more signal. Of course, this is very well valued. And because of interference, this is actually a coherent detection technique. And the chances of having interference from another source is very, very low. So how do we detect things here? We manipulate the frequency of light up and down, and the light that we receive, it has a small frequency shift. And because those are beating, when we take the fast Fourier transform, we can see the frequency difference, which is related to the distance and even to the Doppler shift from the frequency. And therefore, we can tell the distance and speed of objects. However, this technique requires complex lasers with narrow line width and tunable lasers, first of all. And we need well-controlled chirp and phase noise. Let's have a look at the platforms that we can use LiDARs with. So the main platforms are flash LiDARs and scanning LiDARs. I'm not going to go into the details here too much. Flash LiDARs work like a camera. They shine light to every direction. They work rapid, but they require more power for longer range. So for long range, we need to scan objects for every single point with high resolution. And when we look deeper into the scanning platforms, there are 4 different main platforms: mechanical platforms, micromechanical platforms, integrated photonics, and hybrid of mechanical platforms and integrated photonics. Here, the integrated photonics option has the highest scalability of production. It is by far the cheapest one, the most robust one, because we don't need any kind of mechanical component, and we can easily integrate this with electronics. However, the design technology is not completely maturized yet, because we are still talking about different approaches of doing this. And mechanical ones are basically, both mechanical and micromechanical. The main problem is that they are fragile, while purely mechanical one is also, on top of that, very expensive because it requires multiple lasers and detectors. However, because of the semi-mature design technology and certain challenges, the hybrid technique has emerged as an option as well, where one of the scans is done by a mechanical component instead of both dimensional scans being done by integrated photonics. It's nice, but it's still fragile, of course. So the progress in integrated photonics has started with the need of routing, splitting, and combining light in a waveguide on a chip. What else we can do on a chip? We can also couple the light in and out. We can shape the beam. We can even generate light by attaching a laser by different means, soldering or 3-5 integration. We can control the properties of light. We can change the amplitude, phase, and polarization. And thanks to that, we can miniaturize most of the optical components and modulate the light in a large bandwidth and very rapidly. And for LiDAR, this technology basically means that easy electronic integration, and we can also easily do FMCW technique here because we can split the light and combine, interfere. So the reason why silicon photonics developed in this way is because of data communication, actually. More data means that we need larger bandwidth. And thanks to that, most of the foundries started adopting silicon photonics. And they started scaling up their production. And over the years, especially in the last 10 years, there were more and more fabless companies appearing and more pure play foundries volume, thanks to that. And vice versa, actually. And thanks to this effect, this change in datacom industry, there's a major platform coming up in silicon photonics, and there's an ecosystem appearing. And this is not only useful for data and communication, but this is also useful for sensing applications such as LiDAR, of course. So now I'm going to briefly talk about different steering techniques by using integrated photonics. How can we use integrated photonics to collimate light in different directions? We basically use antennas. So what I refer as antenna can be a grating or can be a leaky wave antenna if you want to direct the light on to the top of the chip, or it can be from the edge of the chip by using just an edge coupler or just a facet. We can actually, one way of doing this is using switch-based arrays where we have several antennas on the chip and we vary the amplitude that we address to each antenna, so we can turn them on and off. It is perfectly feasible for calibration and control. And if we combine this with a lens, we can collimate the light in different direction. And thanks to that, we can have a very wide field of view. However, this technique still requires an extra step of optical alignment and packaging because we need to use a lens. And inherently, it is a lower resolution because we are discretely addressing different angles. Another option is using optical phase arrays, where we manipulate the phase of each antenna. It is high resolution, which of course depends on the size of the array that we are using. We don't need much of an optics here, but it is very hard to calibrate. And the field of view can be limited because of the pitch of the array. And we have pretty high optical losses, photonics losses. So I'm going to give more details about optical phase arrays now, why I was talking about the pitch and the size of the array. When we look at the array factor of an optical phase array, we see a main lobe, which we are interested in, and we see multiple grating lobes. The position of grating lobes define the field of view in this axis. And besides that, there's next to the main lobe, there are also side lobes. So the main rule of phase array is that the larger the array is, it's like an aperture, basically, the higher the angular resolution is going to be, and we will have a better collimated light. However, the calibration is harder because of the number of antennas, and we will need a lot of power. So another important factor is the pitch of the array. The smaller it is, the better it is. We'll get a larger field of view because the grating lobes are going to be further and further away and even disappear if the pitch is less than half lambda. But there's cross-coupling problem with the neighboring antennas. And then there's another approach that can mitigate this, which is using non-uniform pitch, but there is a problem of side lobe amplitudes highly increasing. So these are the basics of phase array design. And there are two main types of optical phase arrays. One is 1D optical phase array, the other one is 2D optical phase array. The main idea is that in 1D optical phase array, we can change the angle of light by using the phase modulators and a tunable laser by using the diffractive nature of the antenna. In 2D optical phase array, we can use phase modulators to change the angle in both axes. However, because of the size of antennas that we need to get the light out, the 2D optical phase arrays are large pitch and therefore narrow field of view. So this is a huge culprit actually. And they are complicated, they require complicated control and calibration and very high power consumption because of the number of antennas, number of phase shifters needed. So, but 1D optical phase arrays are also not that easy to achieve, but relatively easier because we can have tunable lasers to scan 1D axis still. So now I'm going to talk about the main challenges of accomplishing an integrated photonics FMCW LiDAR. One comes from the need from FMCW, actually, the laser. We require a narrow line width to have a decent coherence length. Otherwise, we will have a penalty in our signal. And we need, for certain applications, we need wide tuning range from the laser because, as I said, if you are going to use diffractive elements, then the field of view depends on the tuning range of the laser. But most important of all, we need chirp linearization and phase noise, which requires a feedback loop at the end of the day. And the field of view is another challenge to reach exactly because of the laser bandwidth that I mentioned before, but also because of the pitch and the cross-coupling in optical phase arrays. And another challenge is the power consumption. So the higher the resolution we need, as I mentioned before, we need more antennas and phase shifters. But all kinds of phase shifters at the end, when we talk about thousands of phase shifters, it in total come to a huge amount of power, over 3 watts. There are two main types of phase shifters, thermal phase shifters and electro-optical modulators. In case of thermal phase shifters, we have small footprint, but they require high power and they can crosstalk. In case of electro-optical modulators, we have low power needs, which is great, but they are very large footprints, several millimeters sometimes. Another challenge is the calibration of phase shifters. When we have over 1,000 phase shifters with all random phase, it is pretty challenging to set the calibration. And this calibration should also work during operation because the module can go through different temperature cycles constantly. So we need to track the phase of this device. And one other challenge is getting rid of optical losses. There are some inherent optical losses that are pretty hard to get rid of, and they come down to 5 to 10 dB total loss, which is quite huge if you consider that we only get almost 10% of our input signal. And apart from that, in silicon, we have nonlinear losses such as two-photon absorption and free carrier absorption. But there's a way to get rid of this effect by using a dual-layer platform, silicon nitride. I believe in the next talk, the imec platform will show a great future for this one. And packaging is, in my opinion, the main problem, the main culprit over integrated photonics. It constitutes over 80% of costs, and it is responsible for most of the yield reduction, actually, and time reduction, because we assemble things, and then when something goes wrong, we have to just throw it away. And of course, all this assembly was for nothing. And interfacing this chip with electronics or optics using optical alignment, such as active alignment, is actually the most time-consuming one and costliest one. But one very important thing that we need to consider is that we are putting optics, electronics, actually integrated photonics, electronics, and laser in the same package. And heat dissipation is a huge issue, especially if you use a series of thermal phase shifters. So apart from those main challenges, I want to mention one platform that is quite interesting. The integrated photonics chip is used, which makes FMCW detection quite easy. And the main goal here is that avoiding using tunable lasers. So instead of using the array or switch to direct the light into axis, we can use this very same one only in one axis, and for the other axis do the sweep with a mechanical mirror or MEMS mirror. So this technique gets rid of a lot of problems, but it is still mechanical, and the robustness therefore is lower, and it also increases the cost. Now I'm going to briefly talk about our company, Xsilight. We started up from C3 in September 2021. We are located in Shanghai, China, and what we are planning to do is developing 4D sensors for 3D machine vision, drone automation, and ADAS industry. Our main vision is becoming the Swiss knife of this industry, actually, making a compact, long-range LiDAR module. By compact, I mean high throughput, minimal packaging, low cost, and lightweight. And the way to do that, in our opinion, is being based in core technology on optical phase array-based FMCW LiDAR. So what we do is using silicon photonics and near-infrared light and FMCW detection technique, we want to make a cost-effective and scalable platform. This is something that comes from integrated photonics anyhow. And eye-safe, this is thanks to the wavelength range that we are using, and robust platform, again, silicon photonics. But being able to use silicon photonics is all thanks to FMCW amplifying the signal, basically being a more sensitive detection technique. And our status right now is that on the technology side, we are developing our first demo. We are filing our core IPs at the moment and building local and several global partnerships for different aspects such as fabrication, design, technology, or the applications of what we are doing. And we are always open for discussions or collaboration. So you will find my email at the last slide. Please feel free to write me anytime. And from the finances side, we are finalizing the seed round by next month. And but still after that, we are always open for investment opportunities. And we are constantly hiring more and more people for the core team. And we still have several positions open in PIC. Thank you very much for listening. And Pierre, thank you.
Thank you very much, Sarp, for this really well given talk. Personally, I learned myself a lot about it, particularly about the origin of all the compromises when it comes to technology choices in LiDAR. It drives them. I have many follow-up questions, but I will save those for the Q&A session, just so that we get all. But myself, I advise the audience to do the same. The next talk is from Amin. So that will talk about the fabrication challenges for LiDAR and how imec Amin, the floor is yours, and I see you're already sharing your screen.
Okay, Pierre, can you hear me?
We can.
Oh, okay, perfect. Okay, perfect. Thank you. Actually, Sarp, you made my life easy with describing all details about LiDAR, so I don't need to spend that much on the concept, so I can be busy with the technology. Okay, thank you, everyone. I am Amin Abbasi. I am helping on the business side for the photonic activity that we have at imec. We have a different photonic platform. So I will talk about this technology that we are developing at imec. But let's start with maybe one intro slide. Why we are using integrated photonic? Because the cost reason. Main reason is the cost. The mechanical one that already exists, Velodyne Pioneering, for example, they are very costly. And if you want to go for the mass production for consumer market, automotive market, you need to lower the cost to hundreds of dollars, not thousands. So this is the main driver, is to go down in the price, and then if you want to do it, you need integrated solution, and of course it should be also in the wafer scale. So it comes in natural choice is the integrated photonic. So one slide about the imec. We are founded in 1984 in Belgium with now about 5,000 international employee. Revenue about 700 million, but main part of it comes from the industrial partnership. So we are working with plus 600 partners in the market in all domains, LiDAR included, quantum, AR, VR, CMOS scaling. Headquarters is in the, Belgium. So as you can see here, but we have a site also in US and in Asia. The bird eye view from top on the headquarters in Leuven. So you can see, recognize our 200 millimeter line, CMOS line, and also 300 millimeter. 200 is more for prototyping and the production. 300 for the advanced. There we have a immersion lithography, for example, the latest tools for the advanced nanotechnology development. 200, 300 millimeters. It is like almost like a commercial foundry 24/7. The operators working on the 3 shifts. So to also bring up to speed about the market, we do see a huge increase in the market size for the LiDAR. And the big part of it is going to be ADAS, this autonomous driving car, because of the safety reason. If LiDAR can bring 1 extra % safety, people will be willing to pay it if it is low cost. So there is going to be in 2026 report by Wahl that it's going to be a huge increase in the LiDAR market, and I believe consumer market is not included here. That is also being as big as the other markets already. So few challenges that also Sarp mentioned: long range, high resolution, wide field of view, low cost, compactness, non-mechanical. 900 versus 1550, time of flight versus FMCW. So I think in the previous presentation we saw most of this bone of these challenges, but I think the solution or the obvious one is the on-chip LiDAR. So using integrated photonic. So at imec we have 2 platforms. One is silicon photonic and another is silicon nitride. Silicon Photonics is more advanced platform that we have for mainly developed for telecom datacom, but we are going to use this platform for the other application, for example, for life science application, for sensing application. So in terms of LiDAR, you need long range and for application like in the automotive or drone. So here you need high power. And the silicon, as we know, due to 2 photon absorption, you cannot put too much power in it. There, then we are adding silicon nitride waveguide that can you can couple more power, like a watt range power, into the waveguide, and then with splitting tree, you can already dilute your power and then go to the silicon that you have a efficient phase shifter. Up to now, we have a thermal phase shifter and electro-optical phase shifter, but we are working on the novel material like a BTO integration that potentially can be low loss and also low power phase shifter compared with the existing technology. And another platform that we have is standalone silicon nitride. Depending on the application, the customer can choose which one is the benefit for them, beneficial for them. Especially silicon nitride standalone, due to the simplicity and also flexibility of adding materials, it become more attractive. But of course, in the advanced silicon photonics, we have a photodiodes also that reduce the complexity of adding photodiode. Why silicon nitride? It is again obvious choice because of wide transparency windows. It can go all the way from visible to the communication, but maybe related to LiDAR, it is the low loss order of magnitude, or in some cases 2 order of magnitude better than silicon, and also watt class for high power application. Compatibility with CMOS, you can also deposit this silicon nitride layer on top of the CMOS for spectroscopy application or massively parallel LiDAR imaging. On silicon nitride, the good thing about imec technology that we can reach to almost 1 nanometer thickness control over 200 millimeter wafer. So for the designer that the design is sensitive to thickness control, this is like a platform of the choice, because when they dice the wafer, they know that their design will work, their chip will work, all will work similar, because the thickness is within 1 nanometer. And the last on the technology side, it is the laser integration. We know that silicon and silicon nitride, they cannot lace because of band gap, indirect band gap. So we are working actively on the laser and amplifier integration. Different approach like direct growth, transfer printing. The one is more promising is the flip chip bonding, passively aligned flip chip bonding. We are working with Amicra in Germany to do this submicron laser alignment. The few initial results show here the zoom in of that, and also these black dots here are the lasers that are fabricated on a wafer, 200 millimeter wafer. We managed to couple more than 10 milliwatt to the waveguide, and the target insertion loss is below 2 dB per facet. So we are very close to this number, and the idea is even to reduce it to below 1 dB and also reduce the reflection, all the challenges. But the main message here that now we are moving more to the integration of adding light source, detector, phase shifter that make it easy and also low cost. What we have developed, of course, we are working with customers that they have their own design. We cannot share, but these are internal slides that we just used our own platform to show the capability. But customer, based on customer need, it can be goes wide. 32 channel optical phase array using silicon nitride platform. As silicon nitride is high power handling, so light can couple from here, then dilute the power. We transition to silicon. We have an efficient 10 times better silicon phase shifter routing to the antenna. Sarp mentioned that the calibration is challenged. So for that, we have a on-chip calibration technology that we call it phase integrator. Here, the information is in the paper, but basically you can do the interference and come back to the photodiode to do the on-chip calibration before looking at the far field. So this is going to solve the calibration issue. And you can scale it to 512 channel. It shouldn't be a problem. And we did this for the single beam moving, or you can do it on the structure light. That is something like a good trade-off between flash LiDAR and also single beam. So you can produce also this structure light and also sweep them in X and Y direction. In a nutshell, what we have achieved, active phase correction calibration purpose. You can increase the number of emitters. We are working on adding silicon nitride SiC layer for the dispersion management, adding a gain medium. This is actively moving forward. We have a promising result on this one. The one that is also working in progress is the adding low power fast phase shifter, especially ETO, that is internal development activity. On the long side, we are on the long development vision, we are working on the vertical photodiode 6 germanium detectors. So I think that was it. I don't want to spend time on the more slide, but the one that is more important, we could help on the design. We are working with lots of simulation tools, also with the design houses. We have a fully equipped lab for material characterization, wafer scale device characterization, and also 200 millimeter and 300 millimeter CMOS line for both silicon and silicon nitride. Thank you very much. I wanted to be within a time frame, and we'll be happy to answer your questions.
Thank you very much, Amin, for this very insightful talk. I also have lots of questions. It's hard not to ask them right now, but make sure to write them down for the people that have them, or put them in the chat. And so we will treat all of the questions during the Q&A sessions. I think that there could be also nice like interplay between answering the questions from the technology side and from the system requirement side as well. So and finally we have Chiara. Chiara will talk about the actual design part of LiDAR systems using integrated photonics, in particular the optical phase arrays that we have seen in both presenter slides actually. So the floor is yours, Chiara.
Thank you, Pierre. Before I share my screen, I wanted to launch this poll. Let's see if it works. Did you guys receive a question? Okay, so I'd like to see how familiar everybody here in the room is with Python, and that will help me also during the presentation. Okay. Looks like we have 30%, a little bit, 70% yes, so that's pretty good, I would say. So I'll go ahead and share my screen now. Can everybody see my screen? Okay. So as Pierre mentioned, today I'm going to talk about how do you design an optical phase array for integrated photonics. So in practice, if you want to get started into the LiDAR industry, maybe you have a startup, maybe you're starting a PhD in this topic, how do you get started designing such a circuit? So I believe that everybody before me already described very well what LiDAR is about and how OPAs work, but I'd like to say a couple of words more. So optical phase arrays are circuits which are employed to achieve optical beam shaping and steering. So how do we achieve this? So the key point here is that we control the phase or amplitude of these emitters. In this case here, we have this phase shifter that control the phase of the output signal. And this way, we can basically control the direction of the beam. So depending on what is the phase shift in the different arms, we can have the beam steering left and right. One important thing to note is that to achieve coherent emitters, all these different branches have to be fed by a single laser source to have coherent light. And that's why we use here, before this phase shifter, we use a splitter tree that splits the signal equally in certain amount of outputs that we decide. So what are some complicating factors? So because an emitter array consists of a discrete set of elements, these can lead to unwanted side lobes. So you have, instead of only a central signal, you also have some side lobes, and this can, of course, interfere. And so usually these side lobes pop up when the spacing between the emitters is larger than lambda divided by 2. So in this case, we have 4 emitters. The spacing is big, so we have the side lobes popping up. And so how do we get rid of this? So if we put now these emitters a bit closer to each other, then we are reducing the spacing, and we also reduce the presence of the side lobes. And something that has already been mentioned before is there is also a way to control what is basically the size of the beam, the width of the beam. So if we now increase the number of emitters, we can decrease the width of the profile of the far field beam and obtain a narrower beam. Okay, so this being said, we saw in the previous slides, maybe I'll go back a second, that we had a 1D array of emitters. As Sarp already mentioned, we can also have 2D beam steering, and actually Amin mentioned it as well. These are achieved with a 2D array of antennas. There are several applications for these, such as, for instance, low-cost 3D imaging or holography, and many others as well. So the reason why I'm mentioning this again is that today we are going to see how to design an optical phased array, where in output we have a 2D array of emitters. So what do we need in order to be able to design such a circuit? So we need to have a structured flow and a structured file organization so that we can manage all the subcomponents, which are complex on their own, and place them together in a coherent circuit. It's interesting to have parametricity, interesting and important to have parametricity in layout and simulation, because we are dealing with the splitter tree, we are dealing with a certain number of emitters, certain number of phase shifters, and we do not want to have to redesign this from scratch every time we want to change these parameters, because as we saw, they affect the performance of the OPA, and so we want to be able to evaluate what the performance is without having to redesign these multiple times. And we need semi-automated optical and electrical routing, because as we change the number of phase shifters, we want to make sure that the routing remains, let's say, accurate. And because the more phase shifters we have, the more contact paths we have as well, of course. And the same thing accounts for optical routing, as say all the optical elements in the circuit, if they're parametric, they also need to be routed semi-automatically. So what can we do with IPKIS then? So IPKIS is a Python scripting environment, hence why I started with this poll about Python. So I'm happy to see that most of the people in the audience are familiar with Python. And IPKIS covers the whole design flow. The components in IPKIS rely on a single component definition, which is centralized, so that you can smoothly transition between the different design stages, such as component design and circuit design. You have parameter control in layout and simulation. At component level, you can visualize the virtual fabrication, and you can run physical simulations using either Comfer, which is built in IPKIS, or with third-party tools like Numerical or CST Studio Suite. And then you can take advantage of the parametricity also at circuit level. So you keep a tight link between layout and simulation, so you have parametricity in both. And then you can run circuit simulations using Caffe, which is a built-in simulation engine. You can run the simulations both in frequency and time domain. And then when you achieve your finalized circuit, you can, of course, export the full design in GDS. You can also run post-layout validation simulations with Caffe, so you can double check that the circuit you're fabricating is correct. And you can perform netlist extraction. So this being said, now how do we actually design these? So just a heads up, this example is available on Luceda Academy, so it's freely accessible to everybody. So you are able to run this, everything I'm showing today, you can run on your PCs as well. And this example is based on a real PDK, which is the IPKIS PDK for Sayepik Shuksan. Of course, such a circuit can be fabricated using other PDKs as well, such as the imec PDK too. But so this means that this is a real life example. But let's get started. So what are the building blocks we need to design this OPA? First of all, we need a laser source. We need a splitter tree to split our light into a certain number of outputs. Then we need phase shifters. And finally, we need emitters. So let's see how to tackle each of these steps. First of all, a laser source. In this case, it's offered as part of the IPKIS PDK for Sayepik Shuksan. And we have selected the laser that operates at 1270 nanometers. Second, we design a splitter tree. And what is the basic building block of a splitter tree? It's a splitter, of course, a Y branch. So we can use either a predefined Y branch from the PDK. So most PDKs have these splitters predefined with models as well that you can use. Or if you need to have a custom Y branch, you can design it yourself. And within IPKIS, you can design this type of components and run simulations and optimization recipes in order to achieve the layout that you need. So for instance, here, you can see an example of a Y branch, which was layouted in IPKIS. And then from IPKIS, you can automatically launch a simulation in numerical. So the 3D structure of the Y branch is built automatically for you, and the simulation is run. And when the simulation finishes, S parameters are extracted from the simulation. You can then use the S parameters to model your component inside IPKIS. So now that we are done with the component design, so we have a layout and we have an S matrix, we want to use this component inside a bigger circuit. So we have a component, we have a model, and then we place this in a circuit, and this circuit will also have automatically a layout and a model as well. So the way we build the circuit is by using i3.circuit, which is a IPKIS feature that allows you to intuitively define circuits. So what are the steps you need without going too much into the details of the code? So first of all, you define properties, which are parameters. These are very important because are what make your, these are the parameters that make your cell parametric, of course. So these are all parameters that you can change from the outside later on. And then we have the list of all the subcomponents of our circuit. And in default specs, we define placement of our components in space, so their location, and the connectivity between the different components. And then we define which ports connect to the outside world. And this way we obtain our splitter tree, and we can run a simulation which is based on the models of the subcomponents. In this case, we have mostly a lot of splitters, but we also have models for the waveguides that connect the splitters to each other. So the next step is the phase shifters. Here we have a 2D arrays of phase shifters. In this picture specifically, it's a 4x4 array. And we are using this component, which is predefined in the IPKIS PDK for Sayepik Shuksan. So let's look at this more in details. is a parametric spiral. And so why did we decide to use a spiral? Because it's low footprint. Imagine you want to draw a waveguide, a straight waveguide, which is as long as a spiral. It will take a lot more space on your chip than a spiral does. And it also allows to achieve a more efficient thermo-optic effect because the heaters you have to design in order to achieve the thermo-optic effect are shorter and wider than they would be if you use a straight waveguide of the same length. This way you can achieve lower resistance and a reduced drive voltage. All right, and the next step are the emitters. So we will have a 2D array of emitters, and because we had 16 phase shifters, we need 16 emitters, so a 4x4 array. And the main building block of this array is also from the PDK. And I'd like to point out that these circuits are defined in a way that the building block that you use is also parametric. So if you decide to change PDK or design your own component later on, you can just replace the P cell inside the circuit without having to redefine the whole logic of the circuit. And that's the advantage of having a parametric approach and a code-based approach that uses Python. Now we have our components and we want to place everything together. And we use circuit again. So you remember we used i3.circuit for the splitter tree. We use it also for the spirals and for the output creating couplers. And now we take all these different building blocks and place them together using, again, i3.circuit. So we have the laser, splitter tree, the phase shifters, and the emitters, which are all instances of the circuit. And we can place them in space using the placement specifications and define the connectivity between them. And I will get back to the connectivity later and show some examples. And so we place everything together, we obtain this layout. So about the connectivity, the next step is making sure that the optical and electrical routing is working well. So how do we take care of routing in IPKIS? Well, we have built-in connectors. For instance, one example is i3.connect Manhattan, which allows you to draw Manhattan-style waveguides and also electrical wires. So this is an example of how to use Connect Manhattan. You only have to define the start port, the end port. You can define control points in order to make sure that the routing goes through the location that you desire. You can define also other parameters such as what is the minimum length of the straight section, rounding algorithm for the bands, band radius, and so on. And then you obtain such a waveguide. So you just defined the start port here, the end port here. This is our control point, and the band radius will make sure that the bands are, let's say, follow the parameter that you specified. Another type of band is i3.connect band, which you can use for waveguides. It works very similarly, except it draws an S band. In this case, following a spline rounding algorithm. And you can always define use the rounding algorithm that you prefer. We also have other ones available, such as the Euler rounding algorithm. So how do we use this in the circuit? So we perform a parametric semi-automated routing. So now this looks like a lot of complicated code. What the gist of this is that it's all code that allows you to achieve a full parameter control. And also through for loops, you can automatically adapt all the circuit connections to the number of ports and to the location of your ports. Basically, you're just checking, okay, how many phase shifters do I have in my circuit? How many grating couplers, emitters do I have in my circuit? And so how far away do I have to space them depending on their size? How do I have to connect them depending on their location? It is all extracted automatically by using for loops. And so you see here that you have connect band, you have connect band here as well, here you have connect Manhattan, So these are all different parts of the circuit being connected to each other. And this works no matter how many outputs you define. And so this is how you achieve the final circuit, also with the full electrical and optical routing. So let's see an example of that. Okay. So here we are running the example using four rows and 4 columns, like the pictures I showed you so far. You can see all the different building blocks. Is a full circuit. And voila. And next, we can define now 8 number of rows and 4 columns without changing anything else. So this circuit is still defined the same way, but you can see that the number, I don't think I can pause, but the number of outputs has now increased automatically. All the routing has been adapted automatically. So you see now you have 8 rows, and voila. So it's as easy as changing just one number. Next, so now that we have a nice layout, which is parametric, we can change it the way we want. We can run time domain simulations on our circuit. So the way we do this is by defining a test bench. Wait, I'll take my pointer again. We use i3.connect components in order to create a test bench for our full circuit. So we define an electrical input for the laser, electrical input for the phase shifters. This way we can control the excitation of the laser depending on the bias that we apply. And then with the electrical inputs on the phase shifters, we can control the output. We then define a power meter so that we can measure the output light power and the phase change. Let's see this in action. These are a layout, the electrical input, and this is the output. So if you change parameters in the layout of your circuit, then the simulation will also adapt automatically. So to summarize, what have we seen? So we have components, we use components from the PDK. In this specific case, it was a specific PDK, but the approach is exactly the same no matter what PDK or custom library that you create in-house you use. So we had a lot of different components, bond beds, lasers, phase shifters, splitters, grating couplers. All these basic components have a model, and when they're placed in the circuit, they maintain their compact model, and it's used to run circuit simulations by IPKIS. And the way we put them together is by performing circuit design with a 3-dot circuit. And we can use different type of connectors. We have more. You can check out our website to find out more about connectors. But what we use today were connect Manhattan for waveguides and electrical wires, bend the connectors for waveguides, and connect components to create our test bench. As I mentioned at the beginning, this example is available on Luceda Academy. So you can try it yourself, just like I did. And you go on the Luceda Academy website in tutorials, designing with an IPKIS PDK. Sorry, you will find the example for cyclic Shuxan optical phase array. You can contact us for a free evaluation license so that you can also run the script instead of just looking at them, of course. And then to finish, I also would like to let you know that we organize events every month. If you want to keep up to date, you can always check our website or our LinkedIn page, and you can stay up to date by subscribing to our newsletters, which are available in 2 languages. And thank you for joining us, and I hope to see you also the next time.
All right. Awesome. Thank you to all the speakers. I think we really have a great panel of speakers. So I will take questions from the audience first. So I have one for Chiara, I think. That's the first one that is on my list. So the one is, can you calculate the far field of your optical?
Pierre? I think we lost Pierre.
Yeah.
Okay. Just
It was...
okay. Maybe he'll come back.
He's back. Pierre, you are back.
Hi, Pierre.
I'm back. Yeah.
Okay.
No, I was just asking. Oh, Chiara froze, and I asked the audience, "Can you see me?" No, I froze. So the question was, can you use a test bench to obtain the far field response of your OPA? Well. Okay.
The question is for me? You can go ahead, Pierre, if you want.
Okay. Well, the answer is, well, our tools are made to simulate everything that's on the chip. That's what they are made for. So what comes out is a manufacturable die, and what we make, what we simulate is what's on the die. Obviously, using spacings and phase shifters, it's easy to do the Fourier transforms in the far field to actually calculate the far field. It's not very complex math, and you have all the positional information of the grating couplers, and you have their relative phase shifts. So I would say we don't have a in-house tool to do that, but I'd say that to the educated engineer, it would be a very simple script on top. And
so maybe to add on this, I stressed a lot about, I really stressed the Python aspect of our platform during my presentation, and this is one of the reasons. So on top of anything that IPKIS offers, you can use basically unlimited Python packages to perform any kind of mathematical operations, analysis, everything you already do maybe without using IPKIS, you can still do together with IPKIS. So it becomes really very powerful.
Okay, then the next question I think is to, I would say, Sarp, which is more of a technology system question. And the question is about where to place the photo detectors when it comes to the calibration, or maybe actually also Amin could answer. Do you have to put them on chip, or can you also put them off chip?
So there are actually two main ways of doing calibration. One is looking at the far field off chip, as Amin mentioned before, but on chip, where to place them? Actually, we had a paper in imec about that. Amin can also mention that one maybe. So, well, there are many ways of doing it. It's very hard to describe for me at this point, saying, for example, using, for example, any part of the optical phase array, tapping some power out of one of the waveguides and interfering with another. That's the idea at the end of the day.
Right.
So, yeah, to complement that, the best would be to put it exactly before the antenna, because you are building your phase error before via the routing, via the phase shifter. So exactly immediately before the antenna, you can tap it, your power, and then you route it to the photodiode, please.
Makes sense. Then we have a question. The line width of coherent light sources is, of course, sensitive to optical feedback, mainly such as reflections and return losses. Can this be managed on the integrated platform? Is there on the integrated platform? I mean, I suppose that the platform that is meant is the integrated photonics platform technology. Is there, say, an optical isolator equivalent? I mean,
yeah, It is the very, very nice question. So, you know, the reflection is the killer for the laser, for the DFB laser. You lose your line width, you lose your noise ring of the laser. So we are trying to reduce the reflection by engineering the interface. You know, you can have an angle interface to reduce the reflection. You can add the epoxy for index matching to reduce the reflection. But also we are working with the packaging house to introduce the isolator. They are isolators off the chip, off the shelf isolator. They are bulky, so you need to expand your beam to go, and then there are some challenges there. But the on-chip version, I believe there are some scientific paper for that. But at imec, we don't have it in our PDK. Our customer, they are papers, so we don't claim that they are our design. So then, using our technology, customer can do this on chip. But they are way forward for it, let's say, for on chip.
Mm-hmm. All right. Any more questions? Come on. Like, otherwise I'll shoot some of my own, but I'll leave the audience the opportunity to ask questions first. Well, like while you ponder about them, I have one very general question. What is actually the power budget for an automotive LiDAR? And where is it mostly spent in today's systems?
You mean the electrical power budget in that sense? Or
like the total power budget, you know, like how many watts the whole machine system yeah. And where is it spent today? Yeah, that's my question.
It's actually a very fair question. So the power budget can be a few watts. That is still feasible as far as I know for car industry.
Mm-hmm.
However, when we talk about other machines that we can integrate this LiDAR into, then a few watts becomes huge, actually.
Okay, so in practice for the photonics, how many watts are we talking about then? Milliwatts, probably.
Yeah. Exactly.
Yeah, depend on your where. I think the one that Sarp mentioned about FMCW, the beauty of that one is that you need lower power compared with the direct time of light. So with a couple of tens of milliwatt shooting power from the transmitter, you can close your link of 200 meter, 300 meter with 10% reflectivity. Mm-hmm. And then, yeah, you know, the indium phosphide laser efficiency, you have a 10-20% efficiency, you are adding up. You need also, these are thermally sensitive, you are adding also the temperature controller to that one. So I would say the laser and temperature controller, the main power hungry. But yeah, today I was in the meeting, they are the power hungry part for this is these not sensor itself, these are the main computer of the car that they're consuming a lot of power. So I think 10 kilowatt, below 10 kilowatt per sensor, it is still, for the car, it is okay. Not for drone, not for the consumer market, but for car, it is the acceptable.
Yeah, exactly.
Okay. So basically, as long as your sensor doesn't consume as much power as the computer, it eases the life of your in the good. Basically.
Yeah. But one thing to mention is when I mentioned the power consumption, I focused on the phase shifters on purpose because one common way is, as Chiara also mentioned, using thermal optical phase shifters.
Mm-hmm.
So this power turns into temperature, and we need to dissipate this power somehow. Mm-hmm. This is a whole different problem, actually.
Right. Maybe leading to that, I mean, you talked about the BTO, which I suppose have an impact on this. Can you tell more about what it really is and what why it's different?
You know, lithium niobate, it is the well-known modulators in the industry for the high-speed communication. It is the electro-optical material that has a Pockels effect, strong Pockels effect. Mm-hmm. So imagine same, but it is CMOS compatible. Lithium for the CMOS line is the poison, so we cannot introduce lithium. So lithium, no choice for lithium niobate. But now we are working on the BTO, barium titanide. It is the CMOS compatible, so you can deposit this with the MBE tools. It has a even higher Packel's effect than lithium niobate. The challenge is on the etching, deposition. So we are working on it on the 8-inch technology. Again, the LiDAR is not the main driver for that. It's the communication actually. So we are just piggybacking what is done for the communication, much bigger market. So then when it is done, you have it, it is the high speed phase shifter, but also low power. So LiDAR can benefit.
Okay, I see. Okay, great.
Maybe a follow-up question about that. How far do you think we are from integration of integrated BTO in fabrication processes in the fab?
Internal activity moving forward, we are going to test in the waveguide structure these BTOs structure, but I think to be able to add to the photonic platform, it will be maybe 1 year or 2 years from now. So still some for the reliability, all the wafer scale quality control, we need to do more develop.
Any more questions from the audience? No? Maybe one more than myself. I have many, but I have to.
You can send an email afterwards.
Yeah. So it was like Sarp's market segmentation of, you create like these huge categorizations like on 3D modeling versus robots.
Yeah.
And then you kind of switch to the next slide, and I was curious, what's driving this segmentation?
So the segmentation, I was mainly thinking about where we would need basically 3D sensors, right? And I wanted to categorize in basically 2 categories, because when we look at it, either it's about how we want to measure things and see things, where we do 3D modeling for our own understanding, or we do it for machines understanding, so to automate things. So that's why I categorized into 2.
It depends. All right, that makes sense. So
it depends who is trying to understand the data,
the
AI or us.
AI or us, like actual intelligence or artificial intelligence.
Exactly.
Okay. Oh, that's actually a great insight. Thank you. I think, wow, that's really interesting indeed. Well, I think we are approaching the end of our webinar, right on time. I think we have 2 minutes left that I want to use to thank all the speakers and also the audience for contributing to this event. Please tune in on such events that we are to hold in the future. On my side, I want to add one last note, is that we are indeed hiring at Luceda as well. I guess that's common pain of every growing company in photonics is to find motivated people to join our team. So if you are such a person and you want to engage with all the great actors in the photonics community, you can either send an email or add me on LinkedIn and say that you want to join our company, and I'll make sure it gets to the right person. So with that, thank you all the speakers and the audience. I learned a lot today, and I hope you do too. Okay, thank you very much.
Thank you very much for organizing. Bye.
Thank you for joining. Bye.